Hey everybody, welcome to Axiom. Today's topic is Huffman Coding from Design and Analysis of Algorithms. Now, I know this sounds intimidating at first, but I promise you it's actually really intuitive once you see it the right way. Let me walk you through it. To store digital information efficiently, we rely on lossless data compression. The objective is to reduce massive file sizes, mathematically shrinking the memory footprint without losing a single precise character of the original information. Standard computing establishes a baseline with fixed length encoding like the ASCII system. In this model, every single character is assigned the exact same number of bits. This creates massive memory waste. High frequency characters like vowels demand the exact same storage footprint as incredibly rare characters like punctuation marks. A solution to this inefficiency appeared long before the digital age. In the 19th century, Samuel Morse developed variable length encoding. Morse realized that mapping frequent letters like E to very short sequences and rare letters like Q to longer sequences optimized the overall transmission time. Translating this frequency based logic to modern binary data offers a way to reclaim massive amounts of wasted memory. But varying code lengths creates a parsing paradox. If codes are different lengths, the computer loses the ability to know exactly where one character ends and the next begins. Imagine a theoretical binary system where frequent characters are assigned short strings of zeros and ones to save space. This animated diagram illustrates the problem. On the left, uniform 3-bit ASCII blocks flow predictably. On the right, an irregular stream of 1 to 4-bit variable length blocks staggers through the parser. Look at a sequence like 010111. The parser fails to decode it. The system stalls because it cannot deduce if a 1 is a single character, or if the 0 and the 1 represent two separate characters. The ambiguity breaks the decoding process. Solving this requires a strict mathematical boundary known as the prefix-free axiom. The axiom states that no character's binary code can form the start or prefix of any other character's binary code. Adhering to this rule guarantees that a parser can read a binary stream from left to right, instantly identifying characters without ever needing to look ahead or second guess its position. To achieve maximum compression without data corruption, we have to architect a prefix-free code using a specific geometric structure. The binary tree data structure provides the perfect geometric map for executing prefix-free logic. This diagram shows an empty binary tree. The navigation rules are strict. Moving down a left branch adds a 0, and moving down a right branch adds a VO. And moving down a right branch adds a 1. Characters are only assigned to the leaf nodes, the absolute terminating ends of the branches. All internal connection nodes remain entirely blank. By tracing a complete path from the root node down to a specific leaf, the tree generates a character's unique binary code like 011. Because a path terminates permanently at a leaf, it is physically impossible for that specific code to extend further. It can never become the prefix of another character. When passing this tree, the computer reads incoming bits to navigate the branches. The moment it hits a leaf, it outputs the corresponding character and immediately resets to the root to decode the next sequence. The tree structure works, but it presents a massive engineering challenge. There are millions of valid binary tree configurations for any given alphabet. We need a mathematical algorithm to find the single specific configuration that yields the absolute shortest paths for our most frequent characters. In 1952, David Huffman solved this while working as a graduate student at the Massachusetts Institute of Technology. Huffman abandoned the standard top-ground division methods. Instead, he designed a greedy algorithm to build the optimal tree from the bottom up. A greedy algorithmic strategy makes the mathematically optimal choice at the current local stage without factoring in the global future of the system. Consider a sample dataset, a 5-symbol alphabet, or each symbol has an explicitly mapped occurrence frequency. The algorithm begins by initializing each of the 5 characters as independent single-node trees. This diagram illustrates the min-heat priority queue, the engine of the algorithm. It automatically sorts these nodes, ensuring the lowest frequencies always sit at the exit point. This queue enforces the greedy choice. It guarantees that the algorithm will always select and merge the least important data first. This diagram maps the algorithmic process. We begin by extracting the two nodes with the absolute lowest frequencies. These two are merged, becoming the children of a newly created parent node. The new parent is assigned a weight equal to the sum of its children and reinserted into the priority queue. The algorithm enters a recursive loop, continuously extracting and merging the lowest weights into sequentially larger subtrees. The loop terminates when a single root node remains, containing a cumulative weight of 1.0. Building the tree from the bottom up forces the highest frequency symbols to the top, securing the shortest possible binary codes. Extracting nodes from a min heap takes O of log n time. Running this operation across the entire dataset results in a total runtime of O of n log n to construct the complete tree. The greedy choice effortlessly sorts the data, producing the most mathematically efficient tree structure possible for the alphabet. With the structure complete, we can evaluate its performance mathematically. This table calculates compression efficiency. We multiply each character's frequency by its new code length to find average bits per symbol. Summing these values yields exactly 2.25 bits per symbol. Standard fixed length encoding for this alphabet requires a minimum 3 bits per symbol. The Huffman tree achieves a 25% reduction in the memory required to store this specific dataset, saving 3 quarters of a bit per character scales exponentially. Applied to files containing hundreds of thousands of characters, this mathematical advantage reclaims gigabytes of storage. This leaves a theoretical question. Why does a short-sighted greedy decision flawlessly guarantee a global optimum here when it fails in so many other computer science problems? The answer is optimal substructure. If you try to swap any deep node with a higher level node, the total cost of the tree strictly increases. The greedy choice's mathematical perfection is locked in. Because the problem exhibits this optimal substructure, the local greedy merges perfectly construct what is known as the minimum weighted external path length for the tree. This elegant mid-century theoretical proof dictates the reality of modern computing infrastructure. Ubiquitous digital formats rely on variations of this exact algorithm today, including lossless JPEG compression, routine zip file archives, and MP3 audio streams. Huffman coding maps statistical frequency to geometric binary logic, reaching the absolute mathematical limit of lossless. And there you have it, Huffman coding simplified. Remember, understanding the basics is key to cracking exams. Hit like if this helped, subscribe to Axiom for daily lectures, and comment below with any doubts. I read every single comment. See you soon.